So we're going to get started with some basic underwater acoustics for hydrographers. And as noted in the introduction, the reason we're doing this is acoustics are what we use underwater. And if we use it for measuring things, we use it for transmitting data, for determining position. So we need to understand just some very basics of underwater acoustics. The first one we're going to tackle is sound velocity in water. Now, most of you should be familiar with the fact that water layers are quite common in oceans, especially lakes and even some rivers. I can remember doing my first dive on an oil rig off of I think it was off of Cameron, and the top 15 feet it was almost zero visibility and muddy, and then I went into this sort of milky white layer at 15 feet, and then bang at 20 feet it was 80-foot visibility. And that was that fresh Mississippi River water sitting on top of clear Gulf of Mexico salt water. So these layers play a role with our acoustics. They can be determined by temperature. So if you have very warm water over cold water, anyone who's dove up north, especially in the lakes, you get 2 or 3 thermoclines on your way to the bottom. We, in the summertime, this one lake where we found America's oldest intact warship, the summertime water temperature on the surface was 70, 72, and on the bottom it was 32. Quite a difference. Now, well, why do we care about those layers? We'll talk about it. And also, there's an example of the salinity difference. You could get that salinity difference on the surface. We call the temperature difference a thermocline and the salinity difference a halicline. The question was, why do we care? And the reason we care is the speed at which sound travels through water is different for different temperatures and different salinities. So, very warm water, that sound is traveling fast. In slightly warmer water, it's traveling a little slower, and in cold water, even slower yet. And if you look, here's a table of sound velocity. And if we come up here, there's one column, there's temperature in centigrade or Fahrenheit, and then across the top is salinity. And you'll see here, we're at 1,546 meters per second when the water temperature is 86 degrees and the salinity is 35. On the opposite end, at zero salinity and freezing, the velocity is 1,404 meters per second. Okay, Vince, so it travels different speeds. Why do we care? In this most simple sense, if we're doing a hydrographic survey, it doesn't matter if it's single beam or multi-beam, if we don't know how fast the sound is traveling through the water, we're going to get errors in our depth measurements. The sound velocity changes the depth measurement. We need to know what that velocity is to make the correction. In the days before we were able to digitally measure sound velocity, we did it physically. We used something called a bar check. We literally put a metal bar under the transducer at a specific height and determined, is the echo sounder reading properly? And if not, we would adjust it. And we'd lower that bar and adjust it, lower that bar and adjust it. And that's how we determine velocity. Now we physically measure sound velocity, and we correct for that both in single beam, multi-beam, and underwater positioning. So it's an important parameter that we need to be aware of. Now, when it comes to multi-beam, something else happens. For those of you who may not know what multi-beam is, it is instead of taking a single sounding directly under the boat, we're taking dozens of soundings in a fan-shaped beam. We have to know the angle of every one of those measurements. And these changes in speed bend the sound waves. We call that refraction. So just like this pencil in the glass of water appears to be broken, the sound waves at the junction of these layers will bend depending upon how abrupt the temperature changes or the salinity change. And if it's going from warm to cold or cold to warm, that changes whether it bends outward or bends inward. So it becomes a critical measurement in multi-beam, and we have to pay more attention in multi-beam than we do in a simple single beam. This is an important parameter to monitor. And when we start talking about multi-beam surveys, one of the questions that comes up is how frequently do I need to monitor my sound velocity? And that's something we'll talk a little bit about when we go into the segment on multi-beam. So we need to know the sound velocity profile so that A, we can get accurate measurements, and B, when we're talking about multi-beam, know exactly where the measurement was taken. One of the ways we can do the sound velocity profile is something as simple as this little castaway. That's a football-sized sensor, and basically you just put it on the end of a line and drop it down to the bottom and retrieve it. And on the way down and the way up, it will take a reading, and you could see we develop a sound velocity profile, knowing exactly where the sound changes abruptly or if it just changes in general. And that data is then fed into our software, and we use that to make those corrections. One of the things about these little handheld ones, carry spares. So I had friends of mine who were doing a multi-beam survey off the Virginia Capes, and they were using an EdgeTech 6205. They threw the sound velocity profile in, dropped it to the bottom, and they were reeling it back in, and all of a sudden it started pulling back. They got it to the surface, and there was a shark eating it. The shark won, cut the line, and they lost, this $5,000–6,000 sensor. So they put the next one on, and the same thing happened. There's an old saying in the military: 2 is 1 and 1 is none. Spares are way important offshore. As we talked about the multi-beam, if this is our multi-beam transducer, and each one of these is a reading of the depth, we can see how the profile will bend the sound waves at certain levels and alter where it impacts the bottom. And those are critical. So not only do we have to know how the speed is affecting the time, which would affect the distance measurement, but we also need to know the impact point of what you're measuring. If we don't know where that sounding was taken, or we assume it's a straight line, it could be a very different measurement. So one of the things to be aware of as we come over here, this is a Norbit multi-beam system. This is one of their compact systems, and a lot of multi-beam sensors now have an onboard sound velocity sensor. That gives us sound velocity right here at the surface. That's an important factor when working with multi-beam, and it is insufficient for conducting a multi-beam survey. In other words, what do I mean by that? That's not enough. You still need the full profile. You need the surface reading, and having the onboard sensor alerts you to changes. In other words, as you're conducting the survey, conditions may be changing, and we will see those changes in the continuous reading at the surface. We still need to do the profiles. And the more changeable the environment, the more profiles are required. Some other things that are, people don't think about, a lot of the UUVs that are being used have a sound velocity sensor and they're recording that data. So that's, another way to get that data. If you're doing UUV ops, you can be recording some of that data as well and using that to help with your mission, your positioning, and things of that nature. So that's a basic overview of sound velocity and how we use it. Any questions on that?